Dear students, today I am going to discuss about the next important topic, that is current electricity. See, the current electricity is a third topic. So it's a most important topic as in board examination as well as competitive examination point of view. This topic is most important one. Of course, in the previous topics that we have been discussed about the electric charge, electric field, electric potential and capacitor. So after that, that's the current electricity. See, in the first topic about the charge concept that we have been discussed, the charge, if it is in the rest condition, what we call, if the charge is in the rest condition, that is what? Static electricity or electrostatic. That's what we call electrostatics. Charge is at rest. Now, first topic study ಮಾಡಿದ ಹಾಗೆ about the charge concept ಅನ್ನು study ಮಾಡಿದಾಗ charges at rest, that is what we call electrostatic. That's what? Electrostatic. But now in the current electricity we are going to discussion about, see, electric current topic. Of course, see, this charge is in motion. That is what we call, say, electric current. It's a very simple thing. Electric current. Charges at rest, that is electrostatics. Charges are motion, that's what we call current, electric current. The charges, the study of charges in motion constitute that electric current. That's what now? That electric current. How exactly about this electric current? The flow of electric charges in a conductor constitute that electric current, especially that electric current in a conductors. What happens now? Flow of charges in a conductor constitute that electric current. It is just like what happens now. Just we compare with say that water flow of water in a river. Flow of water in a river, say like this, we can able to compare. The charges are in motion constitute, charges are in motion in a conductor constitute that electric current. See, about this topic, the discussion about this electric current concept, the German physicist, say George Simon Ohm, say German scientist, say that Ohm, say G.S. Ohm. See that Ohm, he gave some more that concept about this electric current. What happens now? How exactly? It is similar to, say, heat flow in a conductor. Heat flow in a conductor. In a conductor, that heat is flowing. Exactly in the same way, say that Ohm explained about this particular concept. Of course, about this, the discussion about the electric current or current electricity, we'll discuss some more important concept here. Say the first thing is current carriers. See, current carriers. What actually mean by this current carrier? The charge particles which constitute that electric current in solids, liquids and gases. So far, in this case, the charge particles constitute that electric current in solids, liquids or gases. Those are all the charge carriers. What are the charge carriers in solids, liquids and gases? Sometimes they may be able to ask that 2 mark question or that 1 mark questions. In the competitive examination point of view also, they may be able to ask regarding these current carriers. Current carrier, carry the current carry. That's what no, the charge particle. The charge particle constitute the electric current, especially in the solids, liquids, and gases. Now, what are the current carriers? Solids current carriers liquids current carriers gases current carriers Let me know that first thing. Let me take current carriers in, say, that solid. In solids, what are the current carriers? Let me take in the solids. Of course, let me know in this case. Say the first thing, that conductor. In the conductors, what happens? Conductors, of course, it's a solid. In conductors, what are the current carriers? Conductors means what? As we studied in the first PUC also. The conductors means they must be allow the heat to pass through them. That's conductors. Say copper, say aluminium, iron, silver. These are all the conductors. These conductors, what happens now? What are the current carriers now? In conductors, in which what happens now? That free electrons. See, in conductors, free electrons and ultimately are the valence electrons. Free electrons are, see, valence electrons. Valence electrons. What are the valence electrons? Means what? Valence electrons means outermost, say, electrons. In that orbit, I think you studied about that atom topic in which the concept of the nucleus. Say, in this nucleus, say, nucleus, around the nucleus, that electrons, they must be revolving. See, these electrons, if suppose this orbit is outermost orbit, the electrons, they must be present in that outermost orbit. Those electrons are called, say, valence electrons now. Let me know. In the conductors, free electrons and valence electrons. Free electrons or valence electrons are the current carriers. See, the secondly, say in, so far, insulator. In insulators, what happens? What is meant by that insulators? They are not supposed to conduct the heat. They are not supposed to conduct the electricity. So far, why they are not supposed to conduct the electricity or the heat through themselves? Of course, in the insulators, no free electrons at all. In insulators, no free electrons, hence there is no conduction will be taking place. There is no free electrons, hence there is no current will be taking place. There is no current flowing through it, because insulator, they are not supposed to allow the heat to pass through itself. Means that of course that electric current in this, no current is flowing through these insulators. So far, that is also one of the important concept. That next one, say what we call it in semiconductor. Say semiconductor. Semiconductor. Say partially conducting, partially non-conducting, partially insulating. What are the current carriers in semiconductors? In which both free electrons and holes. Free electrons and holes are current carriers in semiconductors. So far, what are the current carriers in solids? You try to understand. Conductors, what are the current carriers? Insulators, what are the current carriers? And in semiconductors, what are the current carriers? Let me know. Conductors, free electrons or valence electrons are the current carriers. Insulators, there is no free electrons at all. This is the insulating material. No current is flowing. Then in semiconductors, free electrons and holes are current carriers in the semiconductors. See, the next one, say about this particular thing, that's what we call, say, solids in liquids. Liquids, what are the current carriers? See, in liquids, what are the current carriers? Positive ions and negative ions are the current carriers here. See, positive and negative ions. Negative ions are the current carriers now in this case. So far in this case, for a copper sulfate, CuSO4, in which there must be some more that positive ions as well as negative ions are the current carriers in liquid. But that last one, say that gases. In gases, there must be also some current carriers. What are the current carriers in the gases? Of course, in the gases, the electrons and say that positive ions and electrons. See, in this case, positive ions and electrons. Electrons are the current carriers in gases. But in the examination point of view, always they may be able to ask the questions regarding this. See, what are the current carriers? That's a question they may be able to ask in the examination point of view. Even also board examination and also competitive examination point of view, they may be able to ask the questions. You try to perfect what are the current carriers, how to visualize this particular concept, you try to understand now. So after this one, next let us say about the very important concept is that electric current. Now, see here that electric current. Electric current. What actually mean by this electric current? As I told earlier, charges are in motion constitute that electric current. It's a very simple number. So that's what charges are in motion. Say charges are in motion, there must be that electric current. Say we also analysis in this case the rate of flow of electric charges in a particular cross section area of the conductor. See, in this case, let me know that the rate of flow of electric charges in a cross section area of the conductor per unit time, that is nothing but say that electric current. So far, in this case, about this electric current, say that I with that electric current, how to analyze this. Of course, in this case that we must able to analyze, say the charges are in motion. Charges are in motion. Say total charges are in motion and total time taken. Time taken. Say this is what now that electric current. Electric current, total charges, motion or total charges say flowing and divided by the total time taken. So far charges motion and this is the time taken. Say I equal to Q by T. Let me know that it's very important. Say that expression that we may be able to get. Say Q by T also. I equal to Q by T. See, this is the expression for that electric current that what we suppose. The same expression, let me know that if suppose. Say Q, if suppose N be the number of electrons. Number of electrons flowing, say in that particular cross section area of the conductor. Number of electrons flowing in a cross section area of the conductor. As I told earlier, let me know that in a particular time t. This expression, that's what we supposed to know. Say that I equal to Q equal to NE divided by T also. Because Q equal to N into. This is the expression, just you remember this expression, that's what Q equal to any, say, quantization of charge. E value, let me take that E value 1.6 into 10 raised to minus 19 coulomb. Say this is also one of the important expression. Sometimes we are supposed to use to solving these examples, we can able to use this particular relation. This is also one of the important the concept about this electric current. And also in this case about this electric current concept, say that if suppose that electric charges, delta Q amount of charges flowing in some cross section area in that very small time, that is delta Q, we must have the basic concept that average current also. See, this is the conductor. In this conductor, what happens now? There is small area, that's a delta S, delta Q, small area in which the charges are flowing, say very small time delta T. In this cross section, how much that charges? Delta Q. Small amount of charges will be moving. Say in very small time interval delta T, say that I average current flowing through this particular conductor, that is delta Q by delta T. This is also that one of the important the concept. And one more thing, that instantaneous current, you must know that instantaneous current I equal to say dq by dt. Very small current must be flowing through it. How exactly it is? Say about that electric current concept, always we should try to analyze how exactly that electric current must be flowing through it. About that all, as already we studied, I equal to Q by T. Or you can say NE divided by T. Where N is what? Number of electrons flowing in a cross section area of the conductor. E be the what now? Say fundamental charge. T be the time taken. So of course in this case, what happens now? About this particular concept, what is the SI unit of that electric current? See that I equal to Q by T. Q is coulomb. Say the current is, the time is the second, coulomb per second, but we must know that SI, it's a basic fundamental quantity, that electric current, its SI unit is that ampere. Say that ampere is the SI unit of that electric current concept. So far, with reference to that all, that electric current, how exactly you can able to analysis about this thing. See that electric current concept, always you can able to analysis for the next concept, how the electric current is the, whether it's a scalar quantity or vector quantity, that also we can able to discussion now. The direction of electric current here, see the direction of electric current. See the direction of that electric current, you must know that electric current, whether it's a scalar quantity or vector quantity, about this current, whether it's a scalar or vector quantity, which one is correct? The current direction, of course, the current have no direction at all. Because how the current will be obtained? It is because the flow of charges, whether that's positive charges gives the direction of conventional current, that negative charge, the current is known as conventional current when the positive charges are in motion. See, if the negative charges are motion constitute that electronic current, of course, in the current, whether it is the scalar quantity or the vector quantity. Of course, it is not a vector quantity. Say how to say this is a vector. It is not a vector quantity. It is a scalar quantity. But as I told, see the current, the direction, of course, we can say the direction as well as that magnitude. The current is flowing like this. But it is not the vector quantity. The current has no direction at all. It should have the magnitude. But the current must have only the magnitude. It should not have that any direction. So far in this case, how to visualize this? The current do not follow the vector law of addition. You must know that. It's very important now. See, the current, say, not followed, say, vector addition. Let me know that vector law of addition. Not followed vector law of addition. Of course, you know that triangular law of vector addition, parallelogram law of vector addition, polygonal law of vector addition, that we have been studied in the previous that year, say in that particular topic, say in the vectors, the scalars and vectors, in that particular topic that we have been studied, say what is the vector quantity and what is the scalar quantity. The vector quantity, it should have both magnitude and direction. Say the scalar quantity, only the magnitude, but there is no direction at all. So with reference to that all, we must know that in this case, current not follow the vector law of addition. Means not parallelogram law of vector addition or triangular, triangular law of vector addition not followed. How exactly it should be obtained? We can able to analysis for a simple concept in this case. If suppose that 2 ampere current is flowing and here 5 ampere current is flowing, between these two angle is 60 degree. If it is 2 ampere current and it is 5 ampere current, what happens to the total current? The total current is 7 ampere. How can able to use? We can able to analysis for the vectors, addition. How simple scalar addition it is, not a vector. In the vector additions, what happens? Let me know that this is p square plus q square plus 2 times of 2pq cos theta. That cos angle is 60 degree, but it is not supposed to use, not followed here. If suppose that this is also that one more, say that the 3 ampere current and this is say 5 ampere current, what happens? This angle is 90 degree. What happens? What is that? The current in this case now that 8 ampere current. This angle, whether it's a 90 degree, say again the same thing it is. P square plus q square plus 2 times of pq cos theta cos 90, that cos 90 is 0. So now we are supposed to use it. It is just like the scalar multiplication. How? This is the scalar. The current which follows this particular that concept. So far we can able to analysis the current. It should be add up like a say scalar. Hence the current is the scalar quantity. It is not supposed to the vector. Say you try to understand how exactly it is. The current is the scalar quantity and it is not supposed to vector quantity now. Say apart from this, we must know that one of the important concept with reference to this, what we came to know that, say that electric current is the scalar quantity, not a vector quantity. That you should try to analyze. After this one, see, as I told earlier about its SI unit is that ampere. See, SI unit of that electric current is that ampere. So far it's ampere. How to define that 1 ampere now? Definition of that ampere. How to visualize this one? Let me know that electric current flowing through that conductor is said to be that 1 ampere. What happens? If suppose, see that 1 coulomb, say that 1 coulomb charge which is flowing, 1 coulomb charge flows through any cross section area of the conductor in 1 second. 1 coulomb charge flowing, 1 coulomb charge flowing in any cross section of the conductor, flowing cross section of the conductor, cross section of the conductor, say in 1 second now. in say 1 second. It's a simple concept. That is what we call, say that 1 ampere. Say definition of that ampere. Let me know that I equal to Q by T. Say that 1 coulomb charge which is flowing in a cross section area of the conductor in 1 second, that is nothing but this is 1 ampere. The definition of that ampere is also very important. Sometimes they may be able to ask, define the SI unit of that electric current. Many times they may be able to ask. Definition of that SI unit of the electric current means the definition of the ampere. See, ಯಾವಾಗಲೂ ಇಲ್ಲಿ ಕರೆಂಟ್ ಅಂತ ಅಂದ ತಕ್ಷಣ ನಿಮಗೆ ಗೊತ್ತಿರಬೇಕು I equal to Q by T. ಕೆಲವೊಂದು ಸಾರಿ ಕೆಲವೊಂದು ನ್ಯೂಮರಿಕಲ್ಸ್ ಅನ್ನು ನಾವು ಸಾಲ್ವ್ ಮಾಡಬೇಕಾದಾಗ ಕೂಡ ಈ ಕರೆಂಟ್ I equal to dq by dt, that is the instantaneous current. That expression we may be able to use, especially to solving some examples in CET as well as the NEET examination point of view. Even also that JEE, we may be able to use these particular expressions. So far, it's the most important concept always you should try to understand now. So after this, then electric current in a conductor. That's the next concept now. Electric current in a conductor. As usual, we know that conductor. See, the conductor in which what happens now? Free electrons are there. In the conductor, free electrons are there. So now electric current in a conductor. Say, electric current in a conductor. See, electric current in a conductor. For example, you must be able to know that this is the conductor. See, in this conductor, what happens? Say here, that's a plus Q and it's a minus Q. The charges. See, that metals, of course, we must know that metals are the good conductor. So in this conductor, there must be some number of free electrons, they are present. These free electrons, how many? Large number of free electrons. How much? In the conductor, 10 raised to, of course, 10 raised to 28 per meter cube. Per meter cube. This much of free electrons are present in the conductor. In the absence of that electric field, these electrons must be moving in this particular conductor. Of course, that electric field. In the absence of that electric field, there are many more free electrons are present. These free electrons are present in this conductor. They are random motion. All the free electrons present in this conductor, they must be random motion in a conductor. How much that electrons are there? In which 10 raised to 28 per meter cube. So for this much of electrons present in that conductor, these electrons are present in that conductors. These electrons move randomly in this conductor in the absence of that electric field now. So far, how they are moving with reference to that there must be some thermal energy. Say, this thermal energy of these electrons, because of this thermal energy, these electrons, they must be moving randomly in that conductor. If suppose average speed of these, say that electrons, they are moving, that average speed is around 10 raised to 5 meter per second. 10 raised to 5 meter per second. This is the average speed of these electrons. Average speed of these electrons at particular room temperature now. However, that velocity must be distributed randomly in these conductors, and also there must be in all possible directions now. Ultimately, what happens now? In this particular case, whatever these electrons must be present in these conductors, what happens? They are randomly motion. It is because of that absence of that electric field. If suppose when potential difference must be applied between this conductor, what happens? there must be some potential difference must be applied to this conductor. What happens now in this case? There must be some field must be applied. There must be some that electric field. Say that electric field must be applied to this conductor. What happens now? See, this is a conductor. You may be able to take that copper wire, or you may be able to take that any metal conductor. So, in which there must be some potential difference that must be applied. See, there must be some potential difference, that positive as well as negative. That battery we must be able to apply, means there must be some, the field must be applied to this conductor or that metal. What happens now? That electric force, electric field exert on these free electrons. What happens now? See, that electric field will be exerted when we are applying some potential between these two ends. There must be some electric field must be exerted on these electrons. What happens? Initially, those electrons moving random way in all possible directions, randomly. So, these electrons, for example, these electrons moving in randomly, anyhow, these are moving in randomly all possible directions. So far, when we apply some electric field to this conductor or that metals, what happens now? In this case, particularly, all these electrons must be freely move in particular order. How exactly this? So far, that electrons motion will be in this direction. So far, that electric current must be in this particular, the directions, that what we came to know that. How exactly? If suppose that free electrons move, say they collide again and again with the positive ions of that metal, each collision destroys that extra velocity gained by these free electrons. Obviously, in this case, whatever that electrons they are moving, for example, these electrons must be moving, in which what happens, they must be gained some more that energy. So, if this electron will be moving and a collision with this, again this electron will be moving and collision with that one more electron, between these two consecutive collisions, there is some more the time gap. That time gap, what we call it now, say relaxation time now. That is what we call it now, relaxation time. That is denoted by that tau. This is the one more concept, that's what we call average time that an electron spends between two consecutive collision is called relaxation time. Its value is around 10 raised to minus 14 seconds. That is also one of the important concepts. Although these electrons gets accelerated by that electric field, whatever that collision which prevent that velocity from this beginning, it should be what now becoming, it becomes that large one. So that electric field provides very small constant velocity towards, say, the positive terminal, towards that positive terminal, and also say there must be that random motion of that electrons gets, say, what now, in particular order. See, that is what, if the random motion of electrons gets streamlined, that electrons gets streamlined now. So far, in which whatever that average velocity, say average velocity with which these free electrons gets drifted in a metallic conductor under the influence of that electric field, that is the phenomena of, say, drift velocity now. That is the drift velocity. These electrons now. Drift velocity of these electrons. What is meant by the drift velocity? The concept of this drift velocity is the average velocity with which these free electrons gets drifted under the influence of some that external field. So that is what we call the drift velocity. This drift velocity, it is around 10 raised to minus 4 meter per second or 10 raised to minus 5 meter per second. This is the drift velocity of these electrons. It is in that particular order. See, with reference to this, try to understand in this case what is important factor. This is the relaxation time and drift velocity. Thermal velocity, that is 10 raised to 5 meter per second. Of course, that electrons are moving randomly. When you apply some electric field, what happens now? Apply that electric field, whatever that these electrons gets drifted, ultimately it is because of under the influence of that electric field concept. Get the drift velocity. The drift velocity is around 10 raised to say minus 5 meter per second. That is also one of the important concept. Always you should try to analysis. So far, this concept, that's what the electric current in a conductor. That next, that very important concept that I would like to discussion in this electric current is that's the Ohm's law. That Ohm's law that I will discuss in the next session.